When you hit play on your phone, you kick off a split-second relay race of computer science, radio physics, and acoustic engineering. Long before audio becomes a digital file, it starts as pure physical force. Sound is simply compression and rarefaction, invisible waves of pressure traveling through air molecules. Looking at this wave visualization, we can see the two core properties of these pressure changes: frequency, which is the number of vibrations per second and determines pitch, and amplitude, which dictates how loud the sound is. To capture those physical changes, a microphone uses a highly sensitive diaphragm. As the air waves push against it, the diaphragm vibrates, generating a continuous analog electrical voltage that perfectly mimics the physical air pressure. But a smartphone can't easily store continuous analog voltages. It has to take tens of thousands of snapshots of that voltage every second to create raw, uncompressed digital data, known as PCM. This baseline standard creates massive, data-heavy files. This sets up an immediate engineering conflict. We have to force massive amounts of digital data through thin air and then rely on a tiny battery-powered box to perfectly reconstruct those powerful physical airwaves on the other side. To solve the bandwidth problem, the audio passes through a codec. This software acts as an aggressive compressor, stripping away less audible details to shrink the massive file size before it ever leaves your phone. Basic mandatory codecs like SBC prioritize connection stability by ruthlessly removing data. On the other end of the spectrum, premium codecs like LDAC require much higher bandwidth to preserve the high-fidelity detail of the original track. Once compressed, the phone's antenna translates the binary data into 2.4 GHz radio waves, launching them into the air at nearly the speed of light. The 2.4 GHz band is incredibly crowded. These radio waves are flying through the exact same airspace used by your Wi-Fi router, wireless mouse, and keyboard, creating a severe risk of data collisions. To survive this airspace, the Bluetooth protocol uses frequency hopping spread spectrum. As we see in this diagram of a signal jumping across frequency bands, the transmission channel changes 1,600 times every second, constantly dodging interference. Without this channel hopping, the packets would crash, and your audio would become a stuttering, unlistenable mess. The speaker's antenna catches these surviving radio waves, unpacks the digital payload, and feeds the stream directly into the digital signal processor. The DSP is the mathematical brain of the operation. It instantly manipulates the audio, boosting the bass, balancing the loudness, and capping peaks to prevent distortion, all before a single sound is actually generated. Next, the signal reaches the digital to analog converter. As rigid digital steps melt into a continuous line, ones and zeros transform into analog voltage. Higher resolutions give the DAC more precise plotting points, accurately filling in the microscopic gaps left by digital formats. The resulting analog output is exceptionally weak, measuring only in millivolts. It immediately flows into an amplifier to dramatically boost its voltage and current. Nearly all modern Bluetooth speakers use Class D amplifiers. They operate at 85 to 95% efficiency, ensuring the battery lasts for hours and the internal components stay cool, all safely monitored by the battery management system. The digital ghost of the song has finally been resurrected into raw electrical power. But electricity is silent. To actually hear the song, we need a mechanical system moving air. The amplified electrical current flows directly into the speaker driver, specifically entering a tightly wound copper ring called a voice coil. As the current travels through the wire, it creates a magnetic field. This field instantly interacts with a permanent magnet inside the driver, thrusting the attached speaker cone violently back and forth. The physical design of the cone determines what frequencies it can handle. Tweeters feature tiny, lightweight diaphragms to vibrate fast enough for high-pitched details, while woofers require massive cones to slowly push the large volumes of air necessary for deep bass. But a small, portable speaker cabinet naturally lacks the internal air volume required to produce that deep bass on its own. Engineers use passive radiators to compensate. In this cross-section of a sealed box, the active woofer pushes inward, compressing the trapped air. That internal pressure acts like a spring, forcing a secondary unpowered cone outward, multiplying the bass without drawing extra power. In less than 300 milliseconds, your phone crushes an audio file, beams it across a chaotic spectrum, reconstructs the data mathematically, amplifies the voltage, and violently pumps a cone to recreate invisible pressure waves. It is a highly engineered relay designed perfectly to trick your brain into hearing the original physical performance.